Hello gentlemen, welcome to our video on section 10.7, and this is on the kinetic molecular theory of gases. Now in this section we're going to take some time to actually look at how to better identify and define what an ideal gas is, what it really means to be ideal. And we can do this with a set of postulates. So up here is a set of postulates that's going to help us conceptualize a gas. I say conceptualize because we can't really see gases, so it's really all concept. These postulates will explain how we expect gases to behave. It's an expectation. We're kind of just guessing out there with, of course, some concrete evidence. If a gas meets all these expectations, it's called an ideal gas. And ideal kind of hints that it's a theoretical thing, because these are just expectations and we're just conceptualizing. So there are ideal gases, which are going to be stated what they are down here, and there are real gases, which we'll talk about later on. So let's look at our first postulate. The first postulate that we can state to expect what an ideal gas will be is that particles are so small in their volume that their size is negligible in comparison to the size of their container. Meaning if their container is this big, their size is extremely tiny in comparison. The second postulate is that particles are in constant motion and are colliding with the container and one another. And these collisions are elastic, meaning all energy is conserved. So kinetic energy that they have is not lost or wasted. Third postulate is that particles are not involved in any attractive or repulsive interactions. In real life, gases, will pass each other, gas particles, and sometimes they will be attracted to one another or would want to repel one another. But in terms of an ideal gas, there is no attraction or repulsion. They would hit each other and bounce away, no problem, no kind of interactive forces there. In the last postulate, that kinetic energy is proportional to temperature. We should already know that one. But for an ideal gas, this is really important. And the temperature, again, is the measurement of the average kinetic energy of a particle. So we know that kinetic energy, in its formula state here, the average kinetic energy, because we're talking about how it relates to temperature, is equal to 1/2 mv squared. And this velocity is the velocity of the particles, the gas particles that are moving in that container. And it has to be an average velocity because we don't know the actual velocity of one particle. We can just kind of get data to get the overall average of what the velocity of those particles will be. You have to keep in mind that velocity and the mass of the particle will determine our kinetic energy. So in a nutshell, as our temperature increases, so if I have gas increasing heat source, then kinetic energy will also increase. Thus, my average velocity of the particles in that container will increase. Gentlemen, this is the kinetic molecular theory. Take notes on it. It's pretty simple, but lock this down so that when we compare this to real gases, we're prepared for that. Adios. Hello gentlemen, welcome to our video on section 10.8 on molecular diffusion and effusion. Now you may have heard of diffusion before. Diffusion is the spread of a substance throughout a space or throughout a second substance. Now an example of diffusion would be something simple. Let's say we have air freshener, we spray it in the air, and eventually it will leave this concentrated place and diffuse outward and spread throughout the room, making the entire room smell like lavender. Now, what does the diffusion rate depend on? It depends on the temperature of the room and the identity of the gas, the identity of the mixture of chemicals in that particular air freshener. Now, you have to remember, temperature is a measurement of the average kinetic energy of particles. So the average kinetic energy of those air freshener particles is based on the temperature of the room. And kinetic energy can be defined as 1/2 times the mass of that substance times the velocity squared of that substance. So Diffusion depends on temperature. Temperature depends on kinetic energy. Kinetic energy depends on mass and velocity. So let's say, for example, I have two different samples here. I have lavender air freshener. I spray it. At the same time, I spray Kenneth Cole black. Get it, gentlemen? So Kenneth Cole, I spray this cologne, and I ask you this question. If I spray them at the same time, which one reaches you first if you're in the back of the classroom? Well, they're at the same temperature right now, so they have the same kinetic energy. Remember, if they're at the same temperature, temperature is the measurement of the average kinetic energy. So that means they have the same kinetic energy as well. But does that mean they have the same velocity? They have the same temperature, same kinetic energy, but does that infer that they have the same velocity? Maybe, maybe not. Let's check it out. So, kinetic energy of the air freshener is equal to the kinetic energy of the cologne because they are at the same temperature. So that means 1/2 m1v1 squared, this is of the air freshener, I put the ones here to represent air freshener, it is equal to 1/2 m2v2 squared. Now, let's just say I'll give you the answer, the air freshener gets to you first. Then what does that mean? If the air freshener reaches you first, that means it had a faster velocity, right? It's v. This v here was higher than that v because it reached you first. In order to keep this side of my equation and that side equal, the same value, if this v is large, that must mean this v was smaller. Okay, but that doesn't give me equalness on each side. That must mean that this mass had to be smaller, and this mass was larger, meaning the air freshener reached you first in the back of the room because those gas particles had a smaller mass. With a smaller mass, they can have a faster velocity and get to you. So, if it has a higher velocity, it means that it had a smaller mass. So the mass and velocity in these individual equations are inversely proportional. If you have a high velocity, you have a lower mass than the other particles that you're comparing yourself to. This substance has a higher mass and a lower velocity. This is when both substances are at the same temperature, the constant temperature. Okay, that's diffusion. Effusion, similar, but some slight differences here. Effusion is the escape of gas particles through a tiny hole. For example, in a balloon, you've all had balloons before. You blow them up on someone's birthday, and you leave them in the corner, and over a few days, the balloons start to deflate, and you go, well, how is that possible if, there's no hole in the balloon? Well, there are small, microscopic holes in that balloon, and air particles can find their way out of it. So let's say I give you this example. I have two balloons with different gases in them. The gases have different masses because they are different substances. I poke identical holes in each balloon, and each balloon is at the same temperature, room temperature. And I ask you this, which gas will effuse faster? Which gas will leave that tiny hole in the balloon faster? What's the answer? Right, the one with the smaller mass. The one with the smaller mass will effuse faster. Smaller mass usually means smaller volume. You can get through that hole much quicker and at a more frequent rate. But now, second question, how fast? Now that's a different question. And to that, we look back on our relationship between kinetic energy. So if they're at the same temperature, that means they have the same kinetic energy. Ke of the first gas equals Ke of the second gas in the second balloon. And again, we have this relationship. 1/2 mv squared of the first substance equals 1/2 mv squared of the second. Now what we're going to do is actually use a little algebra to our advantage. We're going to rearrange to compare the masses and velocities, meaning get mass and velocity on the same side. If I rearrange this equation algebraically, I can get my velocities on the same side like this, dividing both sides by v2. And I can get my masses on that side together through division. So now I have a ratio of velocities to masses, how they compare to one another. Now I can take the square root of each, because I want to look at velocity, not the velocity squared, of each side, and then I get this relationship here. This is a very important equation. That's why it's boxed. You might want to take note of that. But this tells me the ratio of speeds in relationship to the square root of the masses of those gases. So if I know the identity of those gases, then I know the masses, because when I say mass here, I'm referring to molar mass. Since I know the molar mass of these gases, then I can determine the ratio of their velocities, and I can determine, if I know one velocity, I can determine how fast a single gas is going. Now this equation reflects a law. The law that it reflects is a law called Graham's law. It essentially says in words what that equation says. The effusion, or that equation can also apply to diffusion. So the effusion or diffusion rate of a gas is inversely proportional to the square root of its molar mass. The lighter gas has the higher effusion or diffusion rate. So the gas with the lower molar mass will move faster. It will diffuse or effuse at a quicker rate. Gentlemen, take notes, come prepared to do a little practice with this next class. Adios.